So problem 239 from Griffiths E&M. Two spherical cavities of radii A and B are hollowed out from the interior of a neutral conducting sphere of radius r. At the center of each cavity, a point charge is placed. Call these charges QA and QB. Find the surface charge densities, sigma A, sigma B, and sigma r. The field outside the conductor, field within each cavity, force on QA and QB, and which of these would change if a third charge, QC, were brought near the conductor. So to start, I want to talk about the basic electrostatic properties of ideal conductors. The electric field inside a conductor is zero. Why? Because if a conductor were placed in a electric field, initially in an external electric field, initially the free positive charges would go to the right and the negative ones would go to the left. And eventually these charges would pile up, plus on the right side, minus on the left. And these induced charges would produce their own field, which would exactly cancel out the original field. So induced charges cancel the original field. Charge will continue to flow until this cancellation is complete, and the resultant field in the conductor is exactly zero. And this process happens almost instantaneously. Outside the conductor is a different story, but inside the conductor, the electric field is zero. So rho is equal to zero. The charge density is equal to zero. And this is from Gauss's law. Del dot E is equal to rho over epsilon naught. If E is equal to zero, then rho is equal to zero. So any net charge resides on the surface. That's the only place left. A conductor is also an equipotential. So if A and B are any two points within the surface, say like right here and right here, they're going to have the same potential. And one way we can write this is V of B minus V of A is equal to the negative line integral of E dot dl, and that's equal to zero, or V of B is equal to V of A. Like this. Or another way is the electric field is equal to the negative gradient of V, and that's also zero. Because if V is a constant, the derivative of a constant is zero. And the electric field is perpendicular to the surface just outside the conductor, so it's going to be flowing in a way like, let's say it's a conductor, so like let's say it's a square like that, it's always going to be flowing in a way that's perpendicular. And that's just, and if it's a sphere, it's always pointing outward. I guess that square wasn't a very good example, but from example 2.10, it's saying we have an uncharged spherical conductor, so neutral, and at somewhere inside it has a cavity with a positive charge, and what happens is a negative charge gets induced here, which induces a positive charge at the surface of this sphere. And it tells us that the electric field for this particular example is the electric field is 1 over 4 pi epsilon naught q over r squared r hat. And the conductor conceals from us all information concerning the nature of this cavity, but it tells us the total charge. And with that, I'm going to start 239. So for 239, we have this configuration, and we need to find the charge densities. So we have a charge here. Let's say it's positive. It's going to induce a negative charge at this surface. just as this one's going to induce a negative charge at this surface, and so it's going to induce a positive charge along the conductor surface. So if we want to find sigma, sigma is equal to charge Q over area A. The area of a sphere, surface area of a sphere, is 4 pi r squared, where r is the radius. So sigma A is equal to negative QA over 4 pi a squared. Sigma B is equal to negative QB over 4 pi b squared. And sigma R is a little different. Now, this is inducing a positive charge. This is inducing a positive charge over here. So the total charge is going to be QA plus QB. So QA plus QB, and it's positive 4 pi capital R squared. Okay, great. Now, for our electric field outside. For our electric field outside, I'm just going to draw the conductor. I'm not going to draw the cavities. So we have, let's say this is R, and we want to find outside, so we draw a Gaussian surface. And then we're going to use Gauss's law, which says that E dot dA is equal to the charge enclosed over epsilon naught. So E times 4 pi r squared is equal to the charge enclosed. The charge enclosed is the total charge, so that's QA plus QB is equal to charge enclosed, so QA plus QB over epsilon naught. And that gives us the electric field E is equal to 1 over 4 pi epsilon naught QA plus QB over r squared r hat, where r hat is pointing radially outward of the neutral conducting sphere. So that's part B. Part C, we want to find the electric field inside of these cavities. So to find the cavities, I'm just going to draw the one cavity, and we're going to say that this is to A, and we're going to draw a Gaussian surface that goes to RA. So Gauss's law, E dot dA, is equal to the charge enclosed over epsilon naught, where the charge enclosed is equal to QA. Now, we want to select a Gaussian surface that extends to the surface. Otherwise, we have to take a triple integral and it becomes a fraction of the entire electric field. And I'm just saying that RA is up to a point of, because otherwise it doesn't enclose it. Well, wait, never mind. It encloses the entire charge because the charge is a point charge located at the origin. So we can use Gauss's law in this case, and we don't have to say that this is not, we can say that it's inside. What I was trying to say earlier, it's not going to be a fraction of the electric field. My mistake. It is the entire electric field. So E dot dA is equal to charge enclosed over epsilon naught, because it has the entire charge inside. So E times 4 pi a squared is equal to QA over epsilon naught, where E is equal to 1 over 4 pi epsilon naught QA over RA. Sorry, that should be an RA squared, RA hat. And the same thing for B, because B is also a very similar case as this. We could just swap everything. 1 over 4 pi epsilon naught QB over RB squared RB hat. So this is part B. Part D is asking us the force on QA and QB. So I'll go back to this drawing. This is a neutral conducting sphere. There's no electric field inside here. So there's not going to be a force on QB or QA. It's just going to be 0. So the force is 0. So now imagine we place a third charge QC near this conductor. What changes? So obviously anything inside this conductor isn't going to change. So surface charge densities for A and B are going to change. So sigma A, sigma B stay the same. Sigma R changes and the electric field outside changes. The electric field inside here doesn't change, nor does it change here, nor does the force in between these two change, because there's not going to be a force on these. So we can go back to our calculations for sigma. Sigma R was this. So now what's happening is that we have a positive charge on the outside of this conductor, and it's going to be inducing a negative charge along this conductor. So now sigma R changes to QA plus QB 4 pi R squared, but now we're subtracting QC because of the charge induced. And similarly, because the charge enclosed now by our Gaussian surface, we want to select a Gaussian surface that also encloses QC. Now the total charge enclosed is now QA plus QB minus QC. So now the electric field outside is 1 over 4 pi epsilon naught QA plus QB minus QC over R squared R hat. And that's all. Thanks for watching.